Okay, so I'm going to try to explain how we can respond to question 1248 from page 23 of the Origo 3B book. Okay, so in that question, we're given this function. It actually says f of x is equal to this expression, but here I've written it as y equals this, and I've drawn a graph here, and I've tried to get it looking like it does in the book. Okay, so this is the figure that we're shown, and we're told that Philippe says that he can see that there's going to be precisely 1, 0 to the function. Okay, and we need to explain this. Okay, and then find the 0. So I think that in order to understand this, we should maybe just look at graphs of so-called cubic functions, that is polynomials of degree 3. So in Swedish, tredjegrads polynom. Okay. So what I've done here is I've set up these so-called sliders. So I have this general formula for it writes it as f here. So this is f of x equals, this is the function expression. Okay, so ax cubed plus bx squared plus cx plus d, where I can vary the values of a, b, c, and d using the sliders. Okay, so if it's going to be a degree 3 polynomial, then I know that the value of a is not equal to 0. But if I can choose any other real constants, a, b, c, and d, and then whenever I choose some values, like a is equal to negative 0.3, b is equal to negative 0.6, c is equal to 2, d is equal to 3. Okay, so as soon as I choose values for a, b, c, and d, then I get an example of a cubic polynomial. Okay, so a degree 3 polynomial. So what we can say is that when we write it as ax cubed plus plus bx squared plus cx plus d, that we're writing it in general form, and that there's an infinite family of these cubic polynomials, and that if we choose values a, b, c, and d, then we get a specific member of that family. Okay, and the graph of this for this function is shown here in green. So we see that it goes down like this. Okay, and the zeros of the function are where the graph crosses the x-axis. So we see that there are 3 zeros here. 2 of the zeros are when x is less than 0, and 1 of the zeros is when x is greater than 0. Okay, so and we recall also from a previous lesson that when we have a degree 3 polynomial, then the maximum number of zeros is 3 for the function. Okay, and we see we have 3 zeros here. So what we can do now is just vary the values of a, b, c, and d. So if I allow a to vary, okay, it does it a little bit fast. Okay, so you see that a has the biggest effect there when a is close to 0. Okay, so I'm just going to pause this when we get close to 0. Then, like that. Okay, so let's see what happens when we hold the other values constant and we vary the value of b. Okay, I don't really know how to describe this. I guess, you know, pictures as 1,000 words. So we just let the pictures describe this, yeah? So if you were to try to, describe how the value of b affects how the graph of the function looks for a degree 3 polynomial, you see it would be quite a difficult task. Okay, so let's try with C now. Okay, and let's try with D now. So you see that D is perhaps the easiest one to interpret. The D value just moves it up and down in a vertical direction. Okay, so that means that when D is negative 0.1, then the graph is 0.1 units lower in the y direction than it is when D equals 0, for example. Okay, so to describe all this would be quite a very challenging task. But really, the main points that I wanted to show here is that even though we have this infinite family of functions, and even though we saw quite a few graphs that looked a little bit different there, then they all had something in common, and that was that the uh, the number of zeros is at most 3. Okay, and that we can also get uh, precisely 1 0. Okay, so we get that in a situation where we have a so-called local maximum or minimum, in this case, both, um, on the same side of the x-axis. And that means that, if this were higher up, then it would hit 3 times. But since this is below the axis, we're just getting 1 0 here, yeah? So basically, these cubic functions, these degree 3 polynomials, they can have either 1 or 3 real roots. Okay, and what else can we say? Well, when the value of a is negative, then the graph will start up near the top left and end up near the bottom right. Whereas when the value of a is positive, then we get the opposite pattern. It will start near the bottom left and finish up near the top right. Okay, so it will always end up, it will always have this kind of diagonal sort of shape. Okay, that if it starts in the bottom on the left, then it will finish on the top on the right, and vice versa. Okay, so that means that we always get at least 1 0. Okay, and then whether we get 3 or not depends on whether these, whether we have these turning points and whether they're on opposite sides of the axes or not. Okay, so if we get back now to this question 1248, then the graph looks like this. So we know that we have this cubic polynomial, and we know that this value of a is equal to negative 1. So that means that we have this situation where the graph starts up in the top left somewhere and finishes in the bottom right somewhere, relatively speaking. So then that means that since it's kind of started up in the top left and it's already come down to a minimum here and then gone back up again, and since we know that it's then going to have a local maximum and then drop back down further over to the right, then we know that we're going to get precisely 1 0. So we know that Philippe is correct. And in fact, if I just try to scroll this, okay, so you see how it looks there, that we have this situation with a local minimum and a local maximum, both above the x-axis, so we get precisely 1, 0 there. Okay, so this is another thing to be aware of. How the graph looks will depend on the graphing window that we have. Okay, so when you're graphing on your calculators, then choosing an appropriate window is one of the the most important skills to practice. Okay, because for example, if you have a window like this, for example, then you don't see any graph at all. Okay, and when you're calculating on your calculators, when you press second calc, and you get it to find the zeros and so on, then it will only do that reliably if the graph is on the screen and if the zeros are on the screen. So getting a good window on your calculator is key. Okay. Now to find the zero for this function, so that was my response to part A. To find the zero of this function, then we just need to find the value where the graph intersects the x-axis. So on your calculators, you have this this zero. I think on this program it's called roots, actually. Okay. So we found that this is the answer to part B. The answer is that the zero of the function is when x equals 12.36. Okay, and we would give this as a value rounded with a certain number of decimal places. Okay, so this was my response to question 1248 from Origo 3B. Thanks for watching.